combinatorial geometry. Earlier, I was just mumbling why I changed from the pure geometry to combinatorial geometry. And it's probably this one can give you some more insight. And then on this one, we are not going to do the normal counting with geometry figures, that kind of thing. I think that's probably less likely to show up in competition. Here, we want to do this with transformation, this type of thing. So basically, this one is not. I'll probably use an example to show you, and we discuss how to like. So show you this one. If we have a square ABCD, and then you have a point inside this ABCD, and then you have a point Q, and then ask you to show exists P1, P2 on ABCD on the side, such that Q is middle point of P1, P2. Right, this type of thing. This is a pretty simple one. I think it's probably a little simpler for YEAMO, even for number one. But how do we prove this? And if you haven't encountered this type of problem, you probably just say, I'll just different result, and then show this how to construct. And then when you do that type of thing, then maybe your reasoning is not rigorous, and then you get point deducted. And the same thing with this year's BAMO 8. I didn't read the whole thing for BAMO 12. So BAMO 8 also is on BAMO 12. That's about the convex quadrilateral thing, right? The same type. So how do we show this one? What we can do is, from the Q, we can draw a parallel line. Let's say parallel to AB, right? And then if the center of this square is O, and then the parallel line, let's say, intercept this one with MN. And then from this O, next, what shall we do? Anyone? Okay, so you had to show that P1, P2 exist. And definitely this has something to do, this has symmetry. So from center, the distance to this MN line, let's call it D. And then next, you could draw this parallel line. And then let's call this one, where should I probably decide? Okay, so probably this, if I do this here and draw another one, and what we can get with this. Midpoint. So you want a midpoint, and midpoint you definitely want to use kind of like a mid segment, that kind of thing, right? So with this one, then you can just easily draw this. And Q is here, right? And then those two are equal. Then what we can do, all you need to do is just draw this line, and then this done. Right. So this is pretty simple. This concept is just trying to move this side, right? Move the PL, move the CD to a line PL, and then make this Q a symmetry on the symmetry axis between those two, and then you definitely get this mid segment. For this one, you also have other way to do this. Right. Here earlier we used this translation, and next let's think about, can we use rotation to do this? Give you, let me draw another one. A, B, C, D. Let's say down here we have a Q. How do we make this Q midpoint? Right. Think about this Q is the midpoint. Then that means if we rotate the P1 to P2, that's 180 degrees. And this A will be rotated to A prime. And this is just like you rotate this whole square about Q for 180 degrees. So you get this thing. This A prime. And then this, you get B prime here, C prime here, D prime here. And then once you rotate it, those two squares intersect. And then those intersection definitely satisfy its midpoint, right? That's pretty simple, but then just hopefully give you some insight. Second problem, this one, like this. You have a closed curve on the plane. We call this one, let's say C. And then you have a point Q inside this curve. And now ask you to prove exists 2 points on C and P1 Q equal QP2. So the same thing. Okay. How do we do this one? What shall we do with this? Very easy, right? If you know this earlier problem, looks identical, and then the first approach, the translation won't help, but then the second approach by a rotation and the two intercept, because it's a closed loop, and then also probably to be more rigorous, we had to say this, the problem should at the beginning should tell you the curve is not self-looping. So that way it will definitely intersect at 2 points. Otherwise you might rotate it and they happen to intersect at the not place. So this is just also rotation. Right. This is the old Putnam problem. Putnam, where I think most of you guys will participate in this one once you get into college. Okay, and the next one, AMO problem. AMO is a number 6 problem. So this one, and at the beginning, this one might be a little hard because this is a solid geometry, but I just say you know the basic concept, right? Like projection onto a plane, that kind of thing. Okay. So it's this one, AMO number 6. That's 4 distinct parallel plane. And then exist a regular polyhedron. Every plane has one vertex. Right. So this problem, immediately you should recognize this pretty similar to a plane problem. We have done this one, and I think most of you should have seen this problem from different places. I mean, me myself, probably I talk about this. Each one of you 2-3 times. So there's like 3 parallel lines and ask you to draw a regular, to draw equilateral triangle. Right? We know how to do that one by rotation. So this one go to space and ask you this regular tetrahedron. So how should we do that? And this one, you understand, we know this problem, this definitely it's related. So like in this next week, I hope it's next week, right? I think it is. Next week, the YEA AMO competition. When you see a problem, and if you, let's say for this one, and you don't know how to prove it now, but then you have a strong feeling this problem definitely related, right? If you think about this same structure, right? It's kind of like there's some mathematical term for those ones. You're going to learn those ones in this category theory courses. I'm not good in that one. I only know very limited, like some of the duality concept, etc. They have some inner relationship, same structure, satisfy the same principle. So this one, you know, this is definitely useful. So you could just on a separate sheet of paper, trying to prove this one. And then, I mean, if it's like this one is just when you out of something to write, you put it down and then trying to see if there's link. And maybe of this one, say we can, you write the proof and then you're trying to think from here, how do we make this into a regular tetrahedron? Okay. Think about this. this regular tetrahedron, and then those 4 faces, and it will intersect with the other three plane. Because if you think about this one it's on a plane, and then a plane that passing through this vortex definitely will cut the other 3 plane, and then the 3 cut will be what we know, right? This is a stereo geometry concept, because this plane are parallel, and then they also, this intersection line also on the same plane, which is this like A, B, C, D. Right, so ABC plane will cut the other 3 parallel planes as 3 lines, and they're on the same line, and they are not intersecting, because otherwise the plane will intersect, contradict to the concept they are parallel. So you can get 3 parallel plane, 3 parallel line. Okay, and then once you get this 3 parallel line, it's looking closer to what we mentioned here. And then next, those 3 parallel line, and because this is a regular thing, if it's regular, can we calculate their distance between those lines? Because this one, when you do that one, when you prove it, and right now we are not doing a construction problem, right? So we are focused on maybe calculating some some relationship, like the angle, the side with the parallel line angle, etc. Right? And so we get this 3 parallel line. 3 parallel line. How does this help us? Anyone can think about projection? Anyone? So this here, when you have this parallel line, you can see you will be able to. I'm not good with this drawing geometric figures. And on this one, you could construct an equilateral triangle. Let's call this A1, B1, C1. And then those A1s on the first intersecting line, call this L1, B1 on the second, let's call it M1, C1 on N1. And then you can calculate the side length. And once you calculate the side length, you'll be able to get its centroid. Right. And then when you get the centroid, think about the centroid distance to this the centroid distance to those the 3 those three different parallel plane, and then what is the distance? That one you could use a projection to figure out, right? And once you figure out that the distance from the centroid to the three parallel planes, and then you'll be able to find out from the centroid to those three vertices. If you know that one, you'll be able to find out the here it's a little. You'll be able to basically, how should I say that one? But you so let's say this way. So if you find out the centroid to the three plane, and then you can show those indeed that the each edge, the projection, you can calculate based on this intersecting on this particular plane, and then the angles is the same. So that means the corresponding side also equal. So that tells you all these six sides are equal, and then they are on the four different planes, and then this exists. This one is an old AMO problem, and right now we don't really you will not encounter solid geometry, so this is less of concern. But I was just trying to demonstrate you if you get something related, and maybe put them in and then put in lemma or something, and trying to think of a way that could lead to your solution. And then if you are lucky, you guess, or you have good intuition, you guess the correct approach, you might get points, right? And right now, because of the new rule, 14 points, you will be honorable mentioned. So every point counts, right? Just do not give up. Try to get first coming in this first day, the goal is I'll just first of all settle one problem, and then I'll try to do one more, right? If you finish two, you should feel happy about yourself, and then you try to fight for the last one. And so that even that means maybe you have to make some guess, right? Because you know the way they grade it, and too much bashing won't get you any point, right? So there's really no need. And I know, I mean, some of you, if you apply summer camp, the summer camp problem, they ask you to show us how you think, etc. And in YEAMO, AMO, they don't want to see how you think. It's just you put it, your word, and of course you prefer this, you already prove it, you know it correct, put it down, and then they will grade based on whatever you put down. And why you think of this, how you think of this, that's not their concern. So you don't need to put on those type of things. Like say why you should start thinking from small cases, or why do you think about special cases? That's just norm. You don't need to explain. Okay, so give you another one, also can. And this is, suppose you have a regular n-gon. right? And we call this C. Okay, and then ask you to prove any n that's a positive integer, there exists a point set Sn. So that's any n point in Sn can be covered by C, but Xn itself cannot be covered by C. How do we prove this one? Right, do we understand this? So this C is a closed range bounded by a regular polygon. And then this just asks you to prove any positive integer, you have a point set, a set of points that any endpoint in this set can be covered by C, but Xn itself cannot be covered by C. So I think why, so this first of all, this why the case, then definitely means you have to shift, rotate this polygon in order to cover this n-gon, this endpoint. But then if all the points, you cannot do that necessary rotation to make sure you cover everything. But right, so this is just ask you, you had the freedom to construct this set. So let's think about what are the sets you want to construct. Anyone has cover them. So definitely this one, you need to construct a set that must intersect with this C. They need to have some common, and then they need to have some part of that point set should be outside this C range, some should be in, right? Because even though you could, what we call the coloring, it's just, you know, that the one to cover that part is like down here C, you can move those. So we think about circle, like say you might think, what about like a second circle? If the second circle, and this is just pretty clear. If you choose the second circle to be the point set, then only like very particular set of endpoint can be completely covered, right? Those should line up. Once you rotate, they should line up with this vertices. And then if you choose an inscribed circle, then every point will be intersected, will be covered. So that's here, we think it should be have a radius somewhere in between. And then how big a radius? And then once we find that radius, can we show that any endpoint definitely can be covered? Right. So anyone can think what radius we should use? You had to think. Choose those points. Let's say, think about this down here. Suppose we have, let me see, probably. Let's say it this way. All right, some in, some out. And then you have to show this one, like if you choose endpoint and how you can rotate this or shift this circle so that will be completely covered. I started here, you can see, if we choose this radius to be anywhere between the in radius and second radius, then the second part and cannot be covered by this, definitely true. But then we just want to see how we can make sure those one completely covered if you have endpoint. So think about, we know this most likely is circle, right? I mean, you might think about another regular polygon, but one thing is regular polygon directly relate with circle, and also two polygons probably interfere with each other. But we should also know this, like the number side for this this original polygon, the C, should matter, right? The more a side you have, right, that's more close to a circle, then the circle you construct should like getting bigger. Right? Of course, because the in radius increase. So let's think about if we have P1 to Pn, those are the any endpoint. And how do we show this? Because the circle, then definitely a rotation should be able to cover them. Let's think about a rotation. If we have a rotation, that means all of this will be time EI theta. And then what we need to show is you have to show this any point to the center should less equal to R. Right? If that's the case, then any endpoint, this criteria satisfied. So with this way, this R should less than PIO, and then less equal to something, the one that it's going to be an expression, right? Expression probably in terms of the number of point is n, and also the number of side of m is number of side of that regular polygon. So you want to satisfy this criteria. So how do we do this one? Yeah. So we want to say this, let us pi. The pi after rotation, if the still stay outside the circle, and that one, we want that one to be small. Right. So that circle, you can see when you rotate it, and yeah, when you rotate this one, and like here, this part, originally is outside, but then if you rotate it, you could make them inside. And so let's think about those points. How did it change? If after rotation, the pi still stay outside the circle, then that kind of rotation, because you have inside, so that theta will belong to n region, right? So let's think about each region. What's their total length, right? The total length for that one, let's think about it. How big is it? You want that one to be small, right? So that's, you want to say, after all of this, right? Because each one, you have a certain, for each point, you have a certain range that will make this thing stay outside this circle, still outside this closed loop C. And then, so you have n point. You want those n points, each point, you have some range, and then you want to make that range smaller. So they add up total, each one, this add up to a total angle. Suppose, let's say, m times theta. Okay, and then you have n of those points. And for the other endpoint, you also have some angles that will make this point stay outside the range. So each one of them, you have the same if we choose the right one. So total, you have n times m times theta. If this one less than 2 pi, that means even if you run out of all those angles that will make some of those points stay outside the closed loop, closed curve, it's still not 2 pi. So there's some angles will make all those points stay inside the curve. So we want to find an expression that will satisfy this one. So what we want to satisfy this. So you want each range preferably less than pi over mn. How do we make this angles when you rotate that point? Like say down here, this, remember this blue one is the point side, right? And then now of this, of course, for this diagram, you have lots of angles that will make any chosen pi stay outside this regular polygon, which is regular square. But if we make this one, if we choose this one smaller, then that one definitely can, this angle will make the pi stay outside this loop, this regular polygon is small. So just choose p over mn. And p over mn, let's think about after rotation. What's the range? For that one, you can try to draw, let's say this way. Suppose we have this circle, and then you have this polygon. And then right down here, this is definitely an angle. Let's think about, in order to make this this one, this outside, stay outside, what angle we should choose? So for that one, you can see we choose this one as a pi over mn. Now, you see that make them stay outside, that will equal to arc cosine, I think. And choose a point, let's say P. So this the radius R over P pi O. That's what, we need to multiply 2 because you have 2 parts. So this one. And then we want to this thing less equal P over M, pi over Mn. And how do we do this one? This part, the 2 of R cosine R over R secant pi over 2mn. And this one less than pi over mn. So that shows you, indeed, if we choose those to be a circle, and then make the radius as a r times secant pi over 2mn, this one, then we can make this, all those invalid angle sum less than 2 pi. So clearly, by rotation, you can make this endpoint all within this regular polygon, and then this problem proved. And this is also a pattern problem, I think. Okay. And next, probably give you a simple one. So if we have any acute triangle ABC, and then we want to let's construct a CVN line, and then ask you if you have a acute triangle ABC, you can always find a point such that it's a CVN line exists a point CVN line open up 90 degrees to this point. Again, this is also another solid geometry problem. Don't know if you guys interested in think about this. Right. Give you any acute triangle, and then just show this. I need a CVN line open up 90 degrees to this point. Okay. So what do we think about this one? It's, if they open up 90 degrees, then this key thing is just notice it will open up 90 degrees to the three sides of this acute triangle. And then in space, that's open up 90 degrees to a side is just like in a circle. Open up 90 degrees to this line segment is a circle in plane geometry. In space geometry, that open 90 degrees will be a sphere with those line segments as diameter. So this one is just trying to show the sphere, three sphere using the three side A, B, A, C, B, C as diameter. They have a common point. If they have a common point, then that point open up 90 degrees, and then it will open up 90 degrees to any line segment on this plane. Right, so that is how we understand this one, and it's solid geometry, so we could like skip it. Okay. Next, give you another one. You have infinite points on a plane, and any two distance is an integer. Prove they all on same line. Right, that's the point collinear. Right. How do we do this one? This is a problem that's pretty technically YEAMO probably will not use this one. I don't know this whether they want you, because this one, you use conic section concept. So I don't know how they distinguish whether should put in the conic section concept in YEA problem or not. I mean, AMO, you encounter that one. So in YEA, if they have this type of problem, it's understandable. So try to show those all those points collinear. What we do for this one, let's try to see. Right. Think about all those points. They form a set. And then you just choose 3 points and see what we can get. So that tells you AB equal R, AC equal X. So like this. In this JMO AMO computation, do not hesitate to make a diagram, because when you try to explain yourself, you might feel that you understand already, that's quite clear to you, but everyone's style of speaking are different from one another. So if you will be lucky if your reader has similar style as you, but you cannot wish for that. So you have to make something, make the reader easy to understand your reasoning. And one important concept is try to use enough diagram, even though that might mean like you use a word and then you use a diagram and then shows, oh, just like in this case, what happened. So down here, this AB, AC, this integer, so you could label this like R, this is S. And then this BC, also integer. Right. Next, see what give you any point. Suppose we have a point V, P. And then that means PA minus PB is integer. Down here, I even can do positive integer. So with the triangular inequality, we know this one definitely less than R. Maybe less equal PB, less equal R. Right? If it's equal, that's already is collinear. But this one. So here, this part, satisfy this. When they satisfy this one, what you get? Hyperbola. So if you get a hyperbola, I think how can we derive contradiction? So if it's equal to 0, that is a perpendicular bisector. So this AB bisector, perpendicular bisector. Bisector. And then you have the family of those hyperbola line. And think about where that point P located. So the point P, if you think of that one, it can either in this one, perpendicular bisector, or hyperbola, or this on side AB. That's the only possibilities. So the P must lie on this one. And then if you think about this AC, the P should also lie on another family of the three cases. So that tells you what? That tells you that any vertices must lie on the intersection of those two group of set. And then two group of set with that one, you have how many possibilities? Because from AB and AC, satisfy this one, you have finite number of hyperbola. And then you have finite number of perpendicular line along with self. So that tells you we can also easily see this. Can any two of them they coincide? And because this ABC are distinct, so they cannot coincide with each other. So that way tells you you have a maximum of how many intersections? A parallel line with a parallel line, at most 4. Right. And then this intersection gave you at most 1. So the total number intersection is finite. So this it's in the range of this P this AB that's and time AC, right? Each one of this different, you get a new family of hyperbola, and then they intersect. They give you at most 4 intersection point. So this plus the line at most 5 number of intersections. Right. And if you didn't think clearly, you probably want to say even more. But anyway, if even more, you will have at most how many? 3. So that's at most give you 9 intersecting point. But you know, some of them they're not going to be intersecting, otherwise lead to contradiction. So correct answer should be 4, but earlier reasoning you think 9 is fine. This one is finite, but then we set infinite point. So infinite point, they're distant or integer, that's impossible. So this showed you this thing is definitely, they must all lie on this line AB, and then this is done. Okay, so let's do a last problem. It's an IMO shortlist problem, 1985 IMO shortlist. So ask you, does it exist 1985 triangles, and each is maximum inscribed triangle of x squared over 9 plus y squared over 4 equal to 1. So how do we do this? And this one also a very simple transformation problem. And this is ellipsis. If this one is a circle, then you know a circle is a regular equilateral triangle. So you could construct infinite many of them. And then a circle and ellipsis, they have transformation. And you can see if we have each one of those equilateral triangle, inscribed equilateral triangles, you could just change them to x and change this one. And if you do this transformation, you can see x squared plus y squared equal 1, change to x squared over 9 plus y squared over 4 equal to 1. And with this transformation, can we find the inscribed triangles area? And to find area, we know you could use you can think it's a improved shoelace problem, or in the future, if you learn this matrices, probably you should know this formula, like give you 3 point on a plane. How do we calculate the area of that 3 point? The area of the triangle formed by 3 point. If you x1, y1, x2, y2, x3, y3, form a triangle. How do we find the area? That one is 1/2 x1, y1, x2, y2, x3, y3. And similarly, if I gave you 4 points, how do you find the volume of that? What shall we do with that one? That same thing, right? Except this the coordinate, change it to 1. This will be a 4×4 instead of 3×3, and then the leading coefficient is 1/6. 3 factorial. This is 2 factorial. So this one, if we do that, you get y1, and then x2, y2, x3, y3. So this one, when you calculate it, take out a common 2/3 out, time with 1/2, you get 1/3. x1, y1, x2, y2, x3, y3. So this equals 2/3 of original area. So that tells you if you just simply change the inscribed equilateral triangle from a circle to an inscribed triangle in ellipsis, they satisfy this kind of thing. And then with this one, definitely you can find infinite many of them. Right? Of course, this one, let's say, reason I mentioned this is suppose if this one is a JMO competition, you do this way, and there's a little bit of risk because, well, first of all, this type of transformation or even that formula, and it's not in every high school math textbook, so you have to decide it, like up to which point you could use it. And I would say this formula, if you clearly express it, you don't need to prove it. Okay? At least you don't need to prove it before you like already solve all three problems, and then you just run out of thing to do. You can prove this kind of thing is, you know, it's true, but it's not very popular. This one, if you know that should be, you should consider it popular, even as a tetrahedral type. But then another thing is this one. When we say inscribed triangle in a circle to an inscribed triangle in the ellipsis, and we say we just simply just do the substitution. And whether this one is correct or not, it's probably better for you to prove it. Right? So like down here, those type of things, like this is, if you happen to learn this concept from one particular problem, maybe you want to write the proof. Right? Here we can think it this way. This is just, say, suppose you have an ellipsis with a equation x minus c1 square over a square plus y minus c2 square over b square equal 1. And then if we just do a compression or stretch with a ratio k equal a over b, right? You compress or stretch this ellipsis and then ask you what is the resulting equation. This one, you can say this. After this one, you will get x minus c1 square plus y minus a over b c2 square equal a square. So for this one, or like our problem, you probably want to say the other way. Give you a circle and then you compress, you get ellipsis. And how do we show this one? Pretty easy. Just all you do, just show any point x, y. After the transformation, you get what? This just compress it. So that's, if you compress this one, then the coordinate will be a over b y. And then all you do, just substitute this one into the original equation. Substitute this into the original here. And then you can solve this. Simplify and show this exactly equal this. So this is just want to say, if you have a problem that you haven't seen those theorem in at least 2 places, then if you want to use it, better put this as a lemma or something, and then prove it like this, like at this level. All right, so I think probably that's it. I mean, this geometry, camera geometry, etc. You could have like even many different varieties, not infinite, just like enough to keep you busy for your high school year. So you don't want to do too much. Just when you see a problem, in trying to think what is the likely approach, right? And try to figure out the exam writer want you to do what. If you can be in sync with the exam writer, then likely your solution will be easier to get and also easier to grade, and you get more point, right? And so once you finish a problem and try to read it to yourself, and then with a critical side, like editor point of view, not trying to convince yourself your solution is correct, but try to question yourself, like why this case, etc. It does clear, and then if it's not clear, what should I do? Sometimes you might not be able to prove it, right? If you have like one thing you definitely cannot get over, but you know this is correct, just take a little bit gamble and then write it down, rather than this like trying to write some things, a lot of things that seem relevant, but then that's not conclusive, or might even including wrong statement. If someone can easily give you a counterexample, then that kind of statement you should not write. I see here whether no, Kalua was not here, but like during the AMO, I read some of those people's exam paper, and well, the concept is correct, but then they put in some statements, and definitely does not look correct. I mean, you know, other people read it, they will question your statement, they will try to think counter examples. So you don't want to leave that kind of vulnerability to your grader, right? So write some things, put all the necessary qualification word, right? So that way, avoid getting deduct unnecessary point. And sometimes you don't want to go to extreme. So that's why I earlier suggest you put in graph to illustrate your concept. All right, so I'll stop here. Thank you. Hope you good luck.